Okay, this is week 4, EE315 Microprocessors, your favorite course. Well, we're going to talk about more arithmetic instructions this week. Actually, now you have an idea of how to write a complete, not a complete, but a partially complete code in which you can create loops. I mean, I know you just seen a single example, and when I ask you to write it on your own, you will have difficulty, but now you can learn how to do it because you have the tools. And next week we'll start the labs. On Monday, your TA is going to show you how to use the Kale, how to debug a code. And starting with this week, I'm going to be sharing some screenshots of Kale. And I will be doing live code sessions on Kale. So the things that you see in your labs, starting with Monday, I'll be demonstrating them on these lectures as well. So you'll get used to using it, and this will help you in your labs and you're studying for the exam. Anyways, okay, let's start. What do we have? Well, we're going to talk about arithmetic instructions. We're going to talk more about conditional branching, and we're going to talk about a new concept called link register. Actually, you will remember it. It was one of the special function registers. You didn't know what it was used for. You're going to learn it, and it's very simple, don't worry. Okay, so guys, I'm going to just pour here a bunch of instructions, and you'll realize that they're just simple. This is a notation used to define an instruction. I mean, as you can see, it says that this is the add instruction. There is optional S, which means if you put this, it will change the flags so that you could do conditional branching. If you don't put this, it won't change the flags. It will just do the operation. What is the operation? The operation is Rn and this second operand plus the third operand, because this is add. And if it was subtraction, it was the second operand minus the third operand. And it is equal to the first operand. However, if you see this sign, this bracket, this set bracket, it means that it's optional. In other words, maybe I should put it to you by showing it on my let me show the speaker view. Okay. So actually, I've shown you this the previous week. So guys, this is, for example, add R0, R0, R1. The operation it's going to do is R0, the new value of R0 will be R0 plus R1, right? It's so simple. An optional usage is, as you see in the slides, is this, guys. These are the same. They do the same operation. So if you see not 3 operands, 2 operands after an arithmetic operation, which is defined that way, that you see in the slides. Let me show you the slides now. Where is the slides? Okay, share my screen. Okay. It means that if you're going to write over some of the operands, you can optionally use 2 operands. Okay, this is the same as subtraction. And this is subtraction. This is reverse subtraction, which is operand minus the other one. Okay, question? No. This is CMP, guys, and CM negative, which is CMP just does this operation, changes the flags, but doesn't write the result to anywhere. So that's why in the comment section, there's no destination register, RD, destination register. The result is lost, but according to the result, which is lost, we change the flags. And the operation is this, the first one minus the next one. And CM negative is compare positive and compare negative. CM negative is this operation. Rn minus the minus of the other one. So that's this operation. You can use this. These are the definitions. Just you use them and that's it. Okay, good. So I continue. Any questions about these new arithmetic instructions? I know it was fast, but okay. I hear you.
Benim var da sorabilir miyim?
Please.
Hocam burada peki adresin içine yazmayacak mı? RD'nin adresinin içine. Yani o virgül dışarıda olması gerekmez miydi acaba?
Well, are you talking about this comma? This comma? Or this comma? Yes, I mean, this comma being outside, are you asking? Yes?
Okay. Evet, yes.
Okay. Yeah, yes, okay. Now, it doesn't matter. I mean, they defined it. You're right. I mean, definitely that it's going to write over this one. But if you don't have this, you don't have the second comma. That's why the comma is also optional. That's why it's inside the set brackets. But it doesn't mean anything because it's also optional. You don't put the second comma, right? You have only one comma in this case. You know what I mean? I guess you get the answer.
Okay. Hocam bir de şey diyeceğim sadece. Bu
Please.
RD'nin adresinin içerisindeki adresine mi yazacak yoksa adresin içerisindeki
Okay.
veriyi mi değiştirecek?
Guys,
Bir şey var.
when we are talking about, good question, thank you very much. Your friend is asking, are we changing the address of RD or are we changing the value inside of RD? Guys, when we are talking about registers, there are no addresses. Registers are registers. They have names, R0. You don't know any address about it. It's about the information inside it. If you're talking about an address, it's either the memory or the instruction memory, okay? Because to access the memory addresses, but about registers, we call them. Look.
Hocam sesiniz gitti.
Why?
Mikrofonunuzda bir temassızlık oluyor herhalde.
Okay,
Cızırtı geliyor.
okay. Is it okay now? Is it okay now?
Hayır hocam yine aynı.
I hope so. Okay, so
Hocam.
is it okay now?
Okay.
Okay.
Hello, hocam, evet.
Maybe I should change this set. Okay, what I was saying is, yes, registers are registers. They don't have addresses. You call them, hey, R1, come here. It's the registers, okay? And remember,
Okay.
the arithmetic logic unit operations, such as these, as you see on the slides, are only executed on the registers. You cannot do an operation on an address, on a memory. You do the operations on registers. That's why when you're doing an operation, you never write addresses here. You write register names or immediate values. For example, what was the immediate value? Let me show you. So it was something like, just let me show you. So I would say instead of R1, I'd say 7, which means R0 is equal to R0 plus 7. Yes. Okay, immediate values or register values. No addresses. You cannot provide. If you're going to provide an address, that's called indexed addressing, guys. If you see this, sorry. No, you don't have index addressing add. If you have str, now we are touching the memory, sorry. Now we are touching the memory, okay? And it's in str or LDR. In arithmetic operations, always the registers and their names. Okay, no, so let's continue. I guess it's settled. Okay, good. Now I continue. You know more operations now. You knew add, you knew CMP. Now you know sub. Actually, you knew sub. You know reverse subtraction now, but you know the definition. You know by definition now. Knowing your definition is something important. Okay, sorry. So guys, I'm going to show you. Sorry, yes.
İzniniz olursa birkaç şey söylesem. Hocam şu an herhalde kameranızdan zoom yaptınız. Şu an sadece ağzınız gözüküyor. Kendi görüntünüzden.
Nasıl yaptım bilmiyorum da.
O senin PC'den kaynaklı kanka, bende normal şu an.
Hocam bir de internetinizde herhalde bir sıkıntı var. Zoom diyor. Bağlantınızın zayıf olduğunu söylüyor hocam.
Tabii yani.
Rıdvan, o senin bilgisayarınla alakalı bir şey. Bizde öyle gözükmüyor.
Ben gözüküyor geçtim. Zoom söylüyor.
Yani
şu an düzeldi.
Yani
Önceden öyle
Ne
gözüküyor,
oluyor?
şu an.
Ya bağlantı sorunu olabilir arkadaşlar. Kimden kaynaklanıyor bilmiyorum. Benden de kaynaklanıyor olabilir. Sizden de kaynaklanıyor olabilir. Yani artık bu online education'da bu var. Zaten kaydedip koyuyoruz. Ben kendi tarafımda kaydettiğim için en azından benimkiler perfectly YouTube'da çıkacak. O yüzden duyamazsanız lütfen gene söyleyin. Ben elimden geldiği kadar yapayım. Yani çünkü bağlantıyla ilgili yapabileceğim bir şey yok. Ama mikrofon kötüyse onu değiştireceğiz. Çaresi yok. Tamam. Okay, I'll get back. Any questions, technical questions? Okay, so guys, actually there's a nice example here. It's a very nice example in which we do an operation. After we do the operation, that's how you test it, guys. And more arithmetic instructions, you can just follow the link. Let me just follow the link. So, I'm going to show you this link. So yes, that's the link. So this is ARM instructions website. So everything explained here and how you're going to read them. So that's, it is from here that I take all the information I put to my slides. You can find any instruction here. So guys, I'm doing a test here. I'm moving a value to R0. Actually, I'm doing something strange. I'm moving a 32-bit value to R0, and it's not going to move. It's going to take only these two. Okay? Then I'm going to do another move. Then I'm going to do an add instruction and test. Okay? If one of the flags changes or not. And this will prove, for example, that move does not move the most significant bits, because this is a negative number, this is a positive number, and this is -2, by the way. If this was LDR, after this operation, the summation would have been 0, and Z flag would be 1. But since I'm using move, these are not going to be moved. It's going to be FE, which is a positive number, 00000 FE, actually. And actually, when you do this move, there are other registers here. You are going to see them. So line by line in Kale, you can debug them. And this Monday, your teaching assistant will show you how to do this. Okay? So this is a demonstration of how you test your code and see the registers and see the flags. This is XPSR is the flag. So on the left-hand side of your screen, Kale, you in real time see what registers values you get or what flags values you get, blah, blah. Okay? Good. So guys, the difference between add and add S is that S causes PSR to change. You already know this. You definitely have a clear idea of what S is for. Without S, there is no change in PSR. Actually, there is a nice code here showing you with LDR now. This is -2 and +2. When you do this with add, at this point, if I'm at this line, I've executed this one. I'm adding -2 to +2, and the result is 0, guys. And after this operation, if S was here, we don't have an S here, I would expect that Z flag would have been 1, but it is not 1 because we don't have S here. We have the exact same operation, guys. If you just debug down and get here, do I have it on slides? Yes. And at this point, I have the Z flag 1, which means actually this S changes the flags. This will be a way of handling how to just imagine you didn't understand something. Okay, how does it work? Does this operation changes the flags, or what value the flag will have, or what register value will I get? Write the code, debug it, and check the registers and see for yourself. You have this capability. You can do this with a card, and actually without a card using the simulator. This usage of the simulator, the usage of the card, usage of Kale, how to debug, how to load a code in your card. Everything will be demonstrated in the first week of the labs. But after the first week, you'll be expected to perform. Okay? Guys, so it's the smallest number, so it's negative number. So there's another test. These are two negative numbers. Two negative numbers summed up, and it's a strange result. There's an overflow, because overflow is the overflow of the negative numbers. So maybe I should talk about C and V bits. I didn't talk about them. Guys, Z and N are actually very simple. Z, if it's all zeros, the result is all zeros. Z flag will be 1, and if there's an S, of course. And if the most significant bit is 1, it's a negative number, most probably. Then N is 1. But there is something I should tell you. This is a bit difficult to understand. Guys, imagine you have a number at register 0. It is all ones. All ones is FFFFFFs, 8 Fs. And, well, the most significant bit is 1. So if this is a signed number, then it must be a negative number, right? But this could be an unsigned number where you have a full number with F. So most significant bit is not a negative signed bit. It's just a value. Which one? Who decides this? Guys, you decide it. You assume those. So you make operations accordingly. You assume if this is an unsigned or signed bit. So somebody, imagine you have written a code and somebody else comes and looks at the registers and sees some numbers. they cannot understand if they are signed or unsigned. They are your assumptions. I know this is a bit difficult to get, but it will be like, well, I'm dealing with only unsigned numbers. I'm going to write a code which works for only unsigned numbers. If you do it that way, then you'll be using full bits. The most significant bit, still a number, not a signed bit. So imagine you're summing up two numbers. A good example is this summation. This summation, guys. This one, yes. If these are two numbers, if they're unsigned, imagine these are two unsigned numbers. If you sum these numbers up, guys, they are going to make a number which is bigger than 32 bits. Well, try to do it. Try to do it. Let's try to do it. Let's try to do it. So this is my number, right? Well, I'm assuming that this is an unsigned number. I'm summing the numbers. The unsigned sum makes 0 with a carry. Guys, if I assume that this is an unsigned number, I call this carry. Okay? That's why in the slides, C bit, carry bit becomes 1. But imagine I assume that these are signed numbers. In this case, this makes a signed number because this is, sorry, this is 8. I'm really sorry, guys. I'm really sorry. I'm really sorry. I'm confusing you. I'm confusing you. So this makes an 8. How does it make an 8? Actually, these are 8s. This is 1 0 0 0 1 0 0 0. You just add these up. It becomes 0 0 0 0 1. So 0 0 0 0 kind of. Okay. So this becomes a carry. This is the carry bit. Guys, imagine this was a signed number in 2's complement because all our signed numbers are 2's complement. I told you before that 2's complement signed numbers cannot be summed up like this. If you sum them up, it will be the same operation. There will be a 1. Well, if it's a signed number, the carry is called the overflow. So in this specific example, for both signed case and unsigned case, whatever your assumption is, there is a carry. That's why in the slides, where are the slides? Both V and C bits are 1. Okay? We can find operations in which we set the carry, but we don't set the V bit. Let's see an example. Let's see an example. Let me show you the screen. I'm sorry, the board. Okay, so guys, I'm assuming that these are 2's complement numbers. So I'm writing a signed number, guys. What is this number in 2's complement negative numbers? Can anybody tell me? What is this number? Any guesses? How did we find out? Do you remember? How did we find the real value of this number?
Hocam 16'ın kuvvetlerini teker teker topluyoruz, öyle değil mi?
If it was an unsigned number, yes. This is a 2's complement signed number, and the most significant bit is 1. So this is minus something. What is the value of this minus something? How did we find out? This is a negative number. I'm telling you, this is a 2's complement. So if it was an unsigned number or a positive number, if this was not 0, it was not 1, it was 0, yes, we would have done that. We are going to do that. But before that, we did something. We have negated all bits. Do you remember that?
Yes.
So this is 1 1 1. This is 1 1 1. This is 1 1 1. This is 1 1 1. Blah blah. All 1 1 1s. 32 1 1 1s. The first was negation. So it becomes all 0, 0, 0, 0, 0, 0, 0, 0, 0, and zeros. And we added 1. Remember how to find the value, absolute value of a negative number? We added 1. Do you remember it from previous slides?
Yes.
Evet.
Okay. Then if it is, the total is 1, then this number must be minus 1. Okay? Everybody get this? Why this
Evet hocam,
number is
anladık.
minus 1. Okay, wonderful. Thank you very much. Now guys, okay, this number is minus 1. If it's an unsigned number, if it is a signed number, it is minus 1. If it is an unsigned number, well, it's incredibly big. It is 2 to the 0 plus 2 to the 1 plus 2 to the... Actually, this number is, this guys, 2 to the 32 minus 1. Well, it's a huge number. Huge, huge, huge number. And that's the largest number you can represent in unsigned notation. Okay? This is unsigned notation. I don't know. Somebody have written a code. Which code they have written? So the other number is, let's say the other number is this. Hexadecimal 1. Well, this is a positive number, so it doesn't matter. It's definitely positive 1. So imagine I'm writing a code, guys. This is R0. This is R1. Okay? And I'm doing this. Add R0, R1. I'm going to sum these values up and write it to R0. The arithmetic logic unit doesn't think of anything. It just sums these values up. So summing them up is very simple. You just put them, maybe I should have done this. Like, şu tarafı gözüküyor değil mi? Evet. I'm just summing them up. So imagine I'm summing these up. How do I sum them? I just put them 0, 0, 0, 0, 0, 0, 0, 1. So guys, actually this is 1, 1, 1, 1. This is 0, 0, 0, 1. If you sum these, 1 plus 1, 1. 1 plus with the carry 1, 0, 0, 0. It goes 0, 0, 0 with a carry. I made the operation fast, but this is how it's done. So arithmetic logic unit creates a carry. This is a carry or an overflow. We will decide. For example, let's see. I mean, there is a carry or an overflow. That's for sure. Because when I sum these up, I had this thing. But is it a carry? Is it an overflow? Or is it both? How do I decide? Okay. So the first thing I do is I make the summation without thinking if it is signed or unsigned. I make it just the summation. Sum these hexadecimal numbers up. And if there is one getting out, I'm saying that there is either carry or overflow. But which one, I don't know yet. Maybe both. Because in the previous case, it was both. Let's now assume that this was a negative number. What is the negative number? Minus 1. What is this number? Plus 1. Minus 1 plus plus 1, which is that number? 0. In the actual summation, is there a carry? I mean, which means the result of the operation, can I still represent this number using 32 bits? Yes, it is 0. You can represent it using 32 bits. So if this is a negative number, if I'm assuming that these are signed numbers, I can still represent the result. That's why this is not an overflow, guys. V should be 0. Because I assume that these are negative numbers or unsigned numbers. This is negative, this is positive. So I assume that the last bit is indicating the sign. When I do the summation, the actual summation is 0. So I can still represent this number. Good. Let's try to do something else. Okay. I do this. I'm now assuming that these are unsigned numbers. So this is not the negative bit. I sum them up. I have a number which is all zeros. If I represent it in hexadecimals, this is 1, 0, 0, 0, 0, 0, 0, 0. So I have an extra digit of hexadecimals. I cannot represent this because in my system it's 32 bits. I can only represent 8 nibbles, not 9 nibbles. So if they are unsigned, the result cannot be represented. That's why the carry is 1. Okay? That's how you decide, guys. Carry and overflow. It's a bit difficult to get first, but you'll get it in time. That's the mechanism. Any questions?
Hocam bir daha anlatır mısınız?
Tabii ki. Now, guys, what we're trying to understand is when the C or V flag will be high. Okay? C or V flag will be high according to the result of the arithmetic operation. The arithmetic operation, whatever it is, does an arithmetic job. What it does is, imagine we are making this example, add R0 to R1 and write it over R0. Okay? And imagine we have these values. First, you don't care if these values are signed or unsigned. I mean, because the last bit being 1 might mean that it is a signed number, or it may also mean that this is a number which is unsigned and it's very big. You don't know yet. Don't care. Just don't care. Do your arithmetic operation. How do you do your arithmetic operation? Actually, doing arithmetic operations is very simple. I mean, I'm going to rewrite this, don't worry. I'm going to do a simpler version of the operation first. I'm going to sum them up. Actually, in binary, this is 1, 0, 0, 0, 1. I do the summation. I don't care about it's being signed or unsigned. So 1 plus 1 is 2. How do I represent 2 in binary? 1, 0, 0, 1 carry. So I got a 1 carry. 1 plus 1 is 2, 1, 0. So 1 carry. 1 plus 1, 0, 0, 1. So there is a carry, guys. That's how I calculate it. Any questions about this part? I guess no. Now I'm going to do it for not a single nibble, but a complete 32-bit nibble, guys. Actually, you don't have to use the binary notation. You can get used to hexadecimal notation, guys. For example, what is F in decimals? Can anybody tell me what is F?
4 tane 1.
Yes, in decimals. That's binary. In decimals. Base 10.
15.
15. Thank you very much. This is 15. 15 plus 1, 16. Can anybody tell me what is 16 in hexadecimals?
1 0.
Thank you very much. 16 in base 10 is 1 0, guys. Everybody okay with this? Any problems with this? Okay. So this is 1. If this is 1 0, it is 2 digits. And you've learned in your primary second class about, I don't know, 15 years ago, that if you have a second digit, you put the first digit, make the second digit as carry. 1 plus F, again, second digit. So 1 carry, 0, 0, 0, 0, zeros. Sorry, zeros. And a 1. Good. The arithmetic logic units has an adder, guys. The adder did a summation. And in the end, there was a carry. So this, I'm calling it carry. There was something residual. I'm not going to call it carry because I don't know if it's a carry and overflow yet. So if there's a residual digit here, I know that either C or V bits will be set. I don't know which one. How am I going to decide? I'm going to teach you now. Up to now, did you get what I did? I just summed these numbers up and tried to find out if there was a residual digit after the most significant bit or digit. After the most, yes, I did. So is this a V or this is C or both? I don't know yet. How do I decide? Now, guys, how do I decide this? C is about signed numbers. V is about, C is about unsigned numbers. V is about signed numbers, guys. Imagine the guy who wrote this code, put these numbers here, and assume that they are signed. Somebody has written this code. And he thought in his mind that when he's writing the code, they are signed numbers. If this is a signed number, what is the value in decimals of this number, guys? We're gonna read. Please tell me, somebody tell me so that I know that you're alive. What is this number in decimals? If it is signed, -1. Okay? Okay. Not okay?
Okay hocam.
Okay. This is -1. If it is signed, I'm assuming that it's signed. The first assumption, do the assumption that it's signed. This is signed or unsigned, it doesn't matter because the most significant bit is not 1. It is 0. So this is +1. If you sum these numbers up, it makes 0. Good. Can I represent a number like 0 in 32 bits unsigned signed notation? Yes. So this carry, this residual thing, cannot be a V bit because V designates if the residual is a signed residual. Because when I do the signed operation, it is 0 and I can represent that number. The problem is with the unsigned case. If this is an unsigned number, this is the largest number I can represent. In 32 bits, is there a number which is larger than this? No, they're all 1. If this something is all 1, you cannot make it bigger in binary, right? Everybody get my point here? And I'm adding 1 to that number. I'm 32 bits, I'm fully 1, I'm adding a 1. And it becomes a 33-bit number, unsigned. Can I represent this 32-bit unsigned number in my 32-bit registers? No. That's why if the operation is unsigned, the 32-bit result is wrong. This carry is trying to tell you that if this is an unsigned operation, the result is wrong. If this is a signed operation, the result is right. Anybody get the point now?
Anladım hocam.
Tabii herkesin de anlaması gerekiyor da. Okay, just watch it again in YouTube and discuss it. I'll try to explain it again. So this is like trying to understand if the result is correct or not. And depending on your operation being signed or unsigned operation, the microprocessor doesn't know what operation you are doing. You could be doing a signed operation, you could be doing an unsigned operation. So in any case, he's telling you both, hey, if you did this operation and if it were signed numbers, it's okay, no problem, you can use the result. But if these were unsigned numbers, the result is not correct, man, because the result is 0 for me, and you're calculating a very big number, unsigned number, which is 33 bits. The guy is trying to tell us that this is wrong using these bits, guys. Okay? Okay, sorry, I was here. So these were the operations. We talked about this. This means that it's optional. You can use either another notation. Şu anda paylaşmış durumdayım, değil mi? Okay, so guys, as you can see, this is an example of showing you that this and this are the same operations. It's adding R0 and R1 to R0. And in the end, the R0 have this value, which is 7, which is the summation. You'll be able to check the results here. So in your left-hand side on Kale, you see the results when you're debugging line by line. Okay, shortly for addition. It's giving you some simple explanations about how V, Z, and C bits are set. So let the 32-bit result R be the result of the operation. So we are summing two things, like just like this one, sub or add, and there's a result. N bit is set if unsigned result is above this value, and signed bit result is negative, and or if the most significant bit is 1. Well, this is a bit confusing, but I'm going to explain it to you. Guys, forget these two lines. If when you make a summation, you don't care if they are unsigned or signed. You just sum them up. If the most significant bit is 1, then N is 1. That's the only thing that you should look for. So what these lines are for, these are explanations. It means that this N bit becomes 1 if the signed result is negative, and this N bit becomes 1 if the unsigned result is larger than this value. Okay? So, okay, these are the results of this situation. You should always check for the last bit. If the most significant bit is 1, N bit is 1. If 32-bit number is all zeros, if all bits of the 32 bits are all zeros, you don't care about carry. Carry could be 1 or not. The residual, you don't care. The 32 bits, they're all 0, then Z bit is set. Okay? V bit is set after a signed addition result is incorrect. That's what I was trying to tell you. You do the addition or subtraction arithmetic operation, you have a result. If that result correctly represents the result that you want to find, then it's okay. In the signed, if it is wrong, for the signed case, V bit is set. If it is wrong for the unsigned case, C bit is set. Okay? Any questions? Okay. Again, for the subs operation, it is explaining the situations. You can do this yourself because these didn't change. I mean, what do we have here is you have a result. You check the most significant bit. If it is 1, n is 0, n is 1. If all zeros you have in 32 bits, z is 1. And B, depending on the correctness of the result, in the case of signed or unsigned, V and C bits are set. Okay? Okay, more on arithmetical instructions. I'm providing you more instructions. This is multiplication. We've used this one multiplied and written over this one. Now you have another instruction with 3 operands, guys. Actually, it's multiply and add. You multiply the first 2, then add the next one. Multiply and subtract. You multiply the first 2 and subtract it from the first one. As you can see, array. This is very important. This one minus this subtraction. Unsigned division, signed division. Very careful. You are doing a division. The value being signed or unsigned will be important. So if your number is unsigned, you are going to use this instruction because you are telling the code what assumption you have. If your numbers are signed, you are using the signed division. Okay, it's doing the same operation, but it is taking into consideration that your numbers are signed or unsigned. So if you're using udiv, and if the most significant bit is 1, the guy won't think that it's a negative number. It will think that it's a whole number with a value. Okay, but if you're using sdiv, the guy will think that the most significant bit is the negation, the sign, and it will do this operation accordingly. Okay, we'll get back to condition codes in the next hour. Any questions?